In this video, we are going to try to predict a product and also to kind of be able to propose the synthetic route for the product by mechanism. So we do have an alkyl halide, and this compound here is called an acetoacetate. So we have the acetone portion, and then we have the ester portion. So we call it the aceto, and then we have the ester from the acetic acid, so acetoacetate. Now, whenever we have an acetoacetate, we need to look at the alpha protons that are more acidic. So in the presence of sodium ethanoate, the protons of this compound here, these protons have a pKa of 11, so which means in the presence of sodium ethanoate, we are going to be able to deprotonate those protons, and then once we generate an enolate, it's going to attack the alkyl halide in an SN2 fashion to install the alkyl group. So we're going to end up with a product that looks like 1, 2, so install an ethyl group in that position. Under basic conditions, this proton is still acidic, so if we use excess, in case we use excess of this alkyl group, we can end up installing 2 of the alkyl groups, but in this case we're only given 1, so we assume that only 1 is installed. In the next, in step 3, so that's the first and the second step. So in step 3, using that and heat, the product that is formed is going to be so when we use an acid, ester will undergo hydrolysis to form carboxylic acid. Then when we heat up the reaction, it's going to lose the CO2. So there's going to be minus CO2. And then we end up forming a ketone. In this ketone, what you can see is we started with an alkyl halide. So we have added 1, 2, 3 carbon atoms to a halide group. So in acetoacetate ester synthesis, we can be able to transform an alkyl halide into a ketone by adding 3 carbons and installing the acetate group. So in other words, we just add an aceto group onto the alkyl halide. Now let us look at the mechanism of the reaction. So in the first step, we have sodium ethanoate, which is OET. Now keep in mind that the alkoxy group that we are using as a base must be similar to the portion of the alkoxy group in the ester, because if we use a different one, we're going to end up forming mixtures. So to maintain the same product, we need to choose the base carefully so it is similar to the alkoxy group of the ester. So the first thing is we're going to do deprotonation. That goes there. And we form 1, 2. That is an enolate. The enolate, now it's going to react with Br. So it's going to do an SN2. So it's going to attack there, kick out the Br. So we install the alkyl group in that position. Now once we install the alkyl group, then we can do hydrolysis, which is going to transform the ester into a carboxylic acid. So with heat, it undergoes a pericyclic reaction. So we had 1, 2, let's have oxygen bonded to hydrogen. And let's have the carboxylic acid portion here. Just put it like that. So then with heat, what is going to happen is that we are going to kick out the CO2, so minus CO2. So these electrons will go here, and that goes here, and that goes to pick the proton, and we end up with a double bond, an oxygen with a hydrogen, and this one undergoes tautomerism to form the product that we were interested in. So we have installed 1, 2, 3 carbon atoms that we have added to the alkyl group that we started with. So in this reaction, keep in mind, we can start from an acetoacetate. In the presence of an alkyl halide, we can transform that alkyl halide into a ketone by installing an aceto group within the alkyl halide.